going to do our wireless section. So this is talking Wi-Fi, so our different Wi-Fi networks and key things you need to know for the exam when talking about wireless network engineering and Wi-Fi in general. So here's on the agenda, we're going to go over wireless networks and overview. We're going to go over different wireless topologies. We're going to go over RF fundamentals, antenna types, and wireless frames. And we're talking about 802.11 frames here. So that's going to be the standard for wireless when we're sending data traffic. So compare that with like Ethernet. That's the 802.3 standard. A wireless frame or a Wi-Fi frame is the 802.11 standard. And you've seen these standards probably before if you've heard of Wi-Fi 6. You know, you go to the store, Best Buy, and they're like, oh, this gaming router has Wi-Fi 7 capability, the new hotness, a Wi-Fi 6 capability. That's an 802.11 standard that defines the speed. But 802.11 is also an IEEE standard, an RFC for it, that describes a wireless frame. We're going to go over the three different types of frames. Okay, so a wireless network utilizes Wi-Fi enabled devices and Wi-Fi emitting network devices to connect end users to the physical network. What do we break that down a little bit? A wireless network is a client that has a Wi-Fi NIC. It has antennas on the client device that are able to talk to the access point emitting the Wi-Fi signal. Wi-Fi is going to come in two major frequencies, and there's a third one now that is out on the market, 2.4 gigahertz and 5 gigahertz. That's the spectrum. On the spectrum, that's what the range we're going to use. 2.4 and 5 gigahertz is Wi-Fi. 6 gigahertz is also a thing now as well. But a wireless network, when we're talking like network engineering, that's how we describe it, a wireless network. Wi-Fi is a common term you hear when talking about wireless communication, and Wi-Fi or wireless networks can be very simple. You can have a simple ad hoc network where we have two users talking to each other. You can have autonomous access point at your house that's just emitting a single SSID, home network dash 2.4 or home network dash 5 gigahertz, and that's it. Just a single SSID that correlates to a single wireless local area network. Or they can be very complex with lightweight and cloud-based access points that are for an entire enterprise with roaming users on multiple floors. And we have to do wireless surveys and heat map scans to look at dead zones. And we have to make sure we're not stepping over each other's frequencies so we have interference. It can get very complex, not only in the wireless field. And what I mean by that, looking at what kind of antennas are emitting, what's our EIRP, what's our SNR, what's the actual signal strength. But then also on the networking side, it can be complex too with different wireless LAN controllers and different types of deployments, different types of robustness, and what kind of security we're going to put on that wireless network. What kind of QoS policies? Are we doing WPA2 PSK or enterprise? And if we're doing enterprise, do we have a good radius or AAA server along with 802.1x for protections? So it can get very complex or can be very simple. Okay, so a wireless local area network contains three major components. It's going to be the access points in conjunction with the wireless LAN controller if we need it, if we're doing like a major enterprise build. A Wi-Fi enabled endpoint, that's just our users, right? And then our distributed network. That's Wi-Fi vernacular, or wireless vernacular for our backbone, our wired connection. Distributed network, that's our switches, right? So if we're on a campus network, that's our access, distro, and core switches. So wireless local area networks use radio frequency and set channels that contain a standardized frequency range in which Wi-Fi enabled devices and access points can use. That's the 2.4 to 5 gigahertz range, and then also the 6 gigahertz range now. And then Wi-Fi signals are propagated via the access points and the antennas within that access points. And there's going to be different antenna standards as well. We're going to have omnidirectional or uni or directional antennas. And then, of course, there's three different modes that access points operate in: lightweight, autonomous, and cloud-based. With autonomous being that access point does everything, and lightweight and cloud-based, it needs some sort of controller. With the cloud-based one, the controller sitting in a cloud service provider. It's a measured service. So like Cisco Meraki, we pay for it. We get a Meraki dashboard that's reachable via the internet. And then with lightweight mode, that's when we have a wireless LAN controller that maybe sits on-prem at our data center, and we have to go into that enterprise intranet to be able to access that wireless LAN controller's GUI to then program our access points. So no matter what the mode, all access points will transmit an SSID, which Wi-Fi enabled endpoints will use to connect to an access point. And on that note, when we talk about SSIDs, remember this. SSIDs correlate to a wireless local area network. And remember that wireless local area network could then correlate to like VLAN 10, which is like the 10.0.0.0 network for our sales team. SSIDs commonly are mistaken like, oh yeah, I'm connecting to the corporate sales SSID, so that's a single access point. And so that SSID equals access point. That's not the case. A single access point can emit multiple SSIDs because those SSIDs correlate to a wireless local area network, okay? So an SSID equals wireless local area network. Also know this, there's going to be a 32 characters max when you set an SSID, and an SSID can be broadcasted using two different standards as recognized by the computer. So what I mean by that, when we're configuring our wireless local area network and we're setting an SSID, SSIDs can be represented in ASCII format or hexadecimal. Don't get too wrapped up in this. What I'm pretty much saying is that when I come click up here, and you see, I look at all my other networks here, that's in ASCII format, but you could represent this in hexadecimal. So I could set my SSID to be broadcasted like a MAC address, okay? That's all that's saying there. So make sure you write those notes down. Oh, let me go back. Okay, let's move on. Okay, let's go over some wireless or Wi-Fi terminology. So an ad hoc network or an IBSS. So it's a peer-to-peer wireless network without a central access point. So this just like computer setting up a signal and another computer connecting that signal and they're talking. Almost like you took an Ethernet cord between two computers and that's it. Okay, that's an ad hoc network. We got a BSS, a basic service set. So a basic service set is a group of devices that communicate with the same access point. So that's just a basic service set represents the SSID you're really connecting to. And that's the building block of a Wi-Fi network. Okay, infrastructure mode. So infrastructure mode is a wireless network that uses an access point to connect to devices. So let me differentiate a BSS between infrastructure mode. Because a BSS, a basic service set, could be done in an ad hoc. That can describe an ad hoc network's range, or can describe an infrastructure mode's network range, the SSID range, I should say. So an infrastructure mode is a wireless network that uses an access point to connect to devices. Basic service area, this is the coverage area of an access point. So this is how strong, where's that signal emitting to, and when does it die out? When does it attenuate, right? So the size of a BSA depends on the signal strength of an access point, and it also depends on the antenna type, the rating of the antenna, how well it emits a signal. So there's a lot of different things that affect a BSA. Look at this ground station here. If it's shooting to a geostationary satellite, the basic service area is going to be that directional. It's going to be directional, right? And it's going to go like 23,000 miles into the sky. It's a big basic service area. If I take a look at my Unify access point I have here, my Ubiquity access point, maybe it spans 100 feet on 2.4 gigahertz range, and that's as far as it'll go, right? So basic service areas really depend on a lot of different factors. Okay, and then SSID is a unique name given to a wireless network. It's used to identify and differentiate between multiple wireless networks. Kind of like I just described there, a single access point can have multiple SSIDs. So an SSID correlates to a network. Then we have the distributed system or distributed network. That's that wired infrastructure, okay? And then a controller. So a wireless LAN controller manages and configures multiple access points in a wireless network. This is for our lightweight AP modes. It provides centralized control and monitoring, and this is where we're going to configure our wireless local area networks and monitor all of our access points and push that configuration down. I talked about this on day one, but remember these lightweight access points are going to connect to this wireless LAN controller over 2 tunnels, a CAPWAP control tunnel and a CAPWAP data tunnel. That CAPWAP control tunnel is going to be how they get their profiles pushed to them. It's how they're managed. It's how they communicate to the wireless LAN controller. While that CAPWAP data tunnel is going to be where all the data frames are sent. That's where we're going to send our user traffic through. Okay, some more terminology. ESS or roaming. So the extended service set is a group of interconnected basic service sets. So that's when we have multiple, like a bunch of lightweight access points in an enterprise, and we enable roaming. So from the wireless LAN controller, we say, hey, these access points are part of this wireless local area network that are emitting this wireless local area network. We're going to enable roaming so that we can have users, doesn't matter what access points they're connecting to, they're going to have a seamless connection. Okay, some RF fundamentals. So RF stands for radio frequency and refers to the use of electromagnetic waves for wireless communication. So if any of you guys in my class are 25 Sierras, that's what I was. This is like our day one shit. And Wi-Fi is the same thing. Radio signals, whether you're manning a UHF, VHF, HF radio, or you're manning a drone via a 2.4 gigahertz range, or you're managing Wi-Fi, RF fundamentals do not change. So RF signal travels at the speed of light and can pass through most objects, but their strength decreases with distance and obstructions, and of course other factors like powers, wattage, and antennas. The unit of measurement for RF frequency is measured in hertz, and then it compounds from there where we have megahertz, gigahertz. So the wavelength of an RF signal is inversely proportional to its frequency, and the frequency determines its propagation characteristics. So RF signals are analog and are modulated to carry information over the air. So look at a single sine wave as a single hertz or a single frequency. The tighter that sine wave, the higher the frequency, but then the more power we're going to need to push out. The longer that wavelength or that single sine wave, the less frequency it has, and the more distance you can cover with less power, but the less data we can put on that wave. I'm trying not to get too crazy. So frequency refers to the number of complete cycles of an electromagnetic wave per second measured in hertz. The frequency band used for Wi-Fi networks is 2.4 to 5 gigahertz. Honestly, guys, okay. What time is it? 10:20. I'm going to move past some of this stuff because it's just, I don't think you're going to need it for the exam, okay? All right. But if you ever want to learn, like, you're like, damn, this is better than what my NCO tells me about SATCOM RF, go watch my video on it. It's pretty good. I took a lot of time making those videos. Okay, now back to more wireless stuff, right? Not just the RF Physics 101 class. So 802.11, that's going to be the frame that we use to carry Wi-Fi. That's the IEEE standard, 802.11. Here's what the frame looks like. So a lot bigger, a lot more stuff going on here than a regular 802.3 frame that you've been used to seeing during this class. When I draw up just a source, destination, MAC address, and it has an FCS field, the 802.11 frame has quite a few more stuff. We're not going to dive too deep into this because what we're going to do now is just quickly go through the different types of 802.11 frames, okay? So we have 3 different 802.11 frame types. We have a management frame, a control frame, and a data frame. Now this is sent between access point and Wi-Fi enabled device. So the first frame we talk about is the 802.11 management frame. And that's going to be how a Wi-Fi enabled device connects to that wireless access point. So this is going to be used for network management tasks. It's going to do control access, authentication, association, and disassociation. So when we add on like authentication protocols like EAP, TLS, this is done with our 802.11 management frame. When we start adding in Wi-Fi protected access, this is talking about, well, all 802.11 traffic, but in the initial authentication is done here in the 802.11 management frame. So here's how a basic image of how we connect to an access point. So from our Wi-Fi enabled device, we send a probe request. We'll get a probe response. That's just pretty much, it's exactly what it says. Hey, we want to connect. Hey, we want to connect. And then we're going to send an authentication request. So if there is authentication on there, this may be like WPA2 PSK, WPA3 PSK, or some enterprise mode. This is where this is done. But if we have open authentication, meaning we have no protections on here, we still send that 802.11 authentication request, okay? Access point sends the authentication response. It says, yeah, you're verified. And then we associate. And then it sends, and that's pretty much saying, okay, cool, we want to talk on this SSID. We want to talk on this frequency range and talk to you, access point. And then they're going to send a response saying, okay. Next is the control frame. So the 802.11 control frame is going to determine when we can and cannot send traffic to that access point. So I kind of skipped it, but wireless Wi-Fi is not full duplex. It uses something called carrier sense multiple access carrier avoidance, and essentially that's half duplex. And we need this control frame to tell us when we can and cannot send traffic to that access point without collisions with our other Wi-Fi enabled devices. Now, obviously, you may think, well, that's crazy because we all connect to an access point. We all talk just fine at my home. We're all sending traffic seamlessly. And that's true. This is just going over the fundamentals. There's a lot more that goes into this to enable multiple different devices to talk at the same time at an access point. This is the fundamentals flow of 802.11 that I'm trying to get through. So 802.11 control frame. This is used for flow control and error checking. It's going to manage traffic. It's going to do power management. And it's going to do frame acknowledgement. And essentially what we have here is a request to send. The access point is going to send us a clear to send. And that's the control frame. This RTS and this CTS. And then this data we send will be part of the 802.11 data frame. So this is going to be used to transmit user data between client and access point. This is going to carry that payload data when I'm sending an email, I'm streaming, I'm accessing a web server. Any of that, that's in the 802.11 data frame. So your normal user stuff, what they're going to be doing on the computer when they're reaching out to the internet. Okay, so that is our wireless overview. Now let's go over the different wireless standards and architectures. And then we'll take a break. Remember, we're trying to cram, okay? So on the agenda, let's go over the different Wi-Fi standards, the different I'm going to skip the AP modes because we talked about this big time day one. I'll just briefly go over it. And then the different wireless LAN controller overview and types. So here's those 802.11 standards I was telling you about with the different frequency ranges and the max data rates. This max data rates, I got this chart offline, and this is like in perfect conditions in a lab environment with zero interference, the best antennas, and the best Wi-Fi enabled receivers. This is the max data rates you can get. You're not getting 6.93 gigabits of throughput at your home and access point doing 802.11 AC. It's just not happening. This is like perfect conditions, okay? But here's our different standards. So when you're configuring this on like a Cisco wireless LAN controller on the GUI, and you're configuring a wireless local area network, and you're picking the kind of 802.11 standards, we call this the different radio channels you want to use. So different radio standards. So 802.11n is Wi-Fi 4, 802.11 AC is Wi-Fi 5, 802.11 AX is Wi-Fi 6, and you can see the different frequency ranges those come in, okay? So 802.11 AC is only in 5 gigahertz. 802.11 AX comes in all three ranges. And that's kind of, you're looking at this chart, that's what you want to memorize for the exam, okay? So autonomous mode. So in autonomous mode, an access point operates independently without the need for a wireless controller. That means the AP is responsible for managing all aspects of that wireless network. On lightweight mode. In lightweight mode, an access point operates under the control of a wireless LAN controller. The wireless LAN controller is responsible for managing the configuration, operation, and security of the wireless network. APs that are deployed, they have to go connect to that wireless LAN controller, and then they're managed from that wireless LAN controller. You can see those two cap-up tunnels here connecting to this wireless LAN controller. We have that control tunnel over UDP port 5246, and we have that data tunnel. That's going to be over UDP port 5247. So lightweight access points are going to split the functionality of an autonomous access point by only taking the role of the real-time functions, meaning that access point is still managing those Wi-Fi connections, so a lab controls the RF transmissions of the frame. Client roaming, association. That's where Wi-Fi encryption and decryption is going to happen at the actual access point. So all that 802.11 management, control, and data frames, that's still happening at the access point, of course, right? Because that's where the Wi-Fi signal is being emitted from. But then when it comes to the actual data and how it's sent, that's going to be on the wireless LAN controller. When it comes to building the profiles and managing what SSIDs get broadcasted, what type of encryption is enforced, that's all done at the wireless LAN controller. So how do LAPs discover wireless LAN controllers? So here's the general flow. A LAP will boot up. It'll build that CAPWAP tunnel, and that control tunnel can be encrypted using something called DTLS. That's still using the TLS cipher suite, but on the CAPWAP tunnel. That LAP will join the wireless LAN controller's network. It'll download its image or its configuration, because we may have to push like actual firmware updates to that access point, and then we download its configuration so we get all of our profiles and what we're going to do as that access point. And then once we're done, we're going to be in what's called a run state. So typically if you do this like in a lab, guys, I wish I hadn't, I want to turn my camera on to show you guys an access point. But it's going to go green, right? That access point is going to go green, or it's going to go blue, depending on, it's going to be like a solid color. And that access point, you can tell by just the colors flashing. You do this enough times, depending on what kind of Cisco access point you have, when you know it's in a good run state. So different methods of discovery. You know what? This is not on the test. Okay, here's that CAPWAP tunnel broken down. Here's what the acronym stands for. Control provisioning of wireless access points. This is a tunneling protocol. So the CAPWAP header encapsulates a regular UDP or TCP packet here, okay? So it's going to encapsulate data between the LAP and controller. So when we're sending Wi-Fi traffic, you know, that access point's connected to a access switch, which is connected to a distro switch, what is then connected to like your wireless LAN controller. Those switches don't see the original TCP UDP packet. They're just going to be seeing this CAPWAP header, right? So it's like a tunnel. It's a tunneling protocol, which is why CAPWAP tunnels can even be built over the web. We can have access points that reach out to a wireless LAN controller that's not on the network. That's actually, you know, at an offsite somewhere being managed by a wireless LAN controller at our HQ. Okay, then we have cloud-based access points. These are managed and controlled through a cloud-based dashboard. These APs are deployed and then provisioned remotely from a like cloud dashboard. So cloud-based access points are well suited for small to medium-sized businesses. So imagine you got like 4 floors, you know, 200 to 300 users. You know, you can use Cisco Meraki. That'll be easy, right? Easy to manage. Okay, this isn't on the, this is more like CCNP stuff. All right, so 30 minutes of me yapping. Let's go ahead and take a 9-minute break. Let's come back at 10:40, and we're going to move on to security. We're going to yap about security for about an hour before we move on to automation. All right, guys, let's go ahead and get started again. So now we're going to go over our security portion of our Cram session. So we're going to go through ACLs, some layer 2 security. Then we're going to go through wireless security, which there I'm not going to dive deep into the different authentication protocols that the extensible authentication protocol framework can do. Mainly, we're going to talk about the Wi-Fi protected access standards and modes. We'll touch on AAA very briefly. Just go over really the acronym, the definitions of it. Touch on the two protocols, Radius and TACX. And then we'll go over IPsec VPNs, tunnel mode and transport mode. I need to hit that. We'll take another break. And then we'll finish up by breaking down JSON, going over how to read JSON and how to say, how many objects are in that JSON object. The nested objects. Is that a string in that variable? Or, in that value? How do you read key value pairs in JSON? Breaking down kind of the dictionary format that it has. So, let's get started with ACLs. So, access control list. We're going to do a quick overview of ACLs, what they're there for, their main purpose, how we can use them in other ways to just define traffic rather than straight filtering. And we're going to go over the different types of ACLs. So we have different types of ACLs, and we're going to go just to the CCNA standards. So I know out there maybe you guys have heard of like multicast ACLs, different actual types, but we're going to stick to like standard and extended. The why, we're going to go over configuration between standard and extended, because standard ACL just uses source IP to filter, while extended ACLs use source destination IP, source destination port, or protocol, and the different how we place them differently as well. And then named ACL, which is just a different way to configure both the standard and extended with a name rather than a number. And that'll be it. So, overview. Access control lists in the Cisco iOS environments, their base function is to filter network traffic based on defined criteria, such as an IP address or protocols. Now, ACLs, when we build them, yes, they're meant to filter, but until you apply them, they're just defining traffic, okay? This is going to come into play when we go over configuration. So ACLs can permit or deny traffic, enhancing network security by controlling access to resources. So they can be applied on routers or switches. Firewalls do the same thing, right? That's just a bunch of ACLs in a firewall. And they can regulate traffic flow and protect against unauthorized access or malicious activity. And then access control entries, or ACEs, those are the permit or deny statements that make up an ACL. So in our pseudo config here, this ACL has 4 access control entries, 3 deny statements, and then an implicit permit at the end that says permit any. So different types of ACLs. So we have a standard ACL. So standard ACLs will only let you filter based on the source IP address. So if we want to filter traffic from VLAN 10 to the SSH server, let's say our SSH server is here, we can only filter based off the source IP. Now, when building a standard ACL, not in named mode, we have a number associated with that ACL, right? So if we create 10 different access lists, 10 different access lists in the standard number range, that would be like access list 1, access list 2. They have a number. So this is the ranges for standard access lists. Standard ACLs, best practice when it comes to placing them, where we actually apply the ACL. Because remember, I can create 100 different access lists with each of them, their first statement being deny all. And they're not going to do anything until I actually enforce that ACL, until I actually put it on an interface and I say, hey, apply this ACL router to this interface and filter at this interface based off this ACL. So with standard ACLs, we have best practice on where to place them. So with standard ACLs, the best practice is to apply the ACL as close to the destination as possible, okay? That's because the access control entries on standard ACLs will only be based on the source IP address. So imagine our security standard here says we just don't want these users to talk to this server over here, okay? So we just don't want them to be able to SSH to these servers. So imagine if, I'm going to grab my pen, if I can find it. I don't know what I did with my pen. All right, whatever. Oh, there it is. So imagine, right, if we can only filter based on source IP. So that means we'll have to say, hey, deny 192 192.168.10.0. And then we create ACLs with the wildcard mask. So a /24, the wildcard mask is 000.255. So imagine we have this deny statement, okay? And we placed it right here at gig 00. We say this ACL, apply it inbound. But it's based off source IP. So it doesn't matter what this computer is talking to. When it makes its layer 3 header, right? This is our layer 3 header here. And that's what we're going to be inspecting when we actually use this ACL. If we say, hey, apply this ACL inbound on gig 01, and the statement is deny 192.168.10.0, any user is going to have all their traffic denied and filtered. So we place the standard ACL as close to the destination as possible because of this, right? Because if we don't, we're going to block everything. So when we place it right here, and we place that ACL outbound, right? We place it outbound, that helps us. That accomplishes, hopefully I'm saying that right, the security standard we have here. We don't want them to SSH to the server VLAN. So here's like a pseudo ACL, how I would do this. The first statement would be deny, and then you do an implicit permit. Another thing I forgot to mention in the ACL overview is that ACLs are in a sequential order. Meaning if I have an ACL, and these are my access control entries, they're in order, 1, 2, and 3. And I put a deny any right here, but then a permit 192.168.10.0/24, and then a permit any. What's really going to happen here is that when I apply this ACL to anywhere on this network diagram, whether it's inbound or outbound on any of these router interfaces, this is going to be the first thing the router looks at when it comes to filtering, and we're denying all traffic. It's not even going to move on to here because this is a deny any. So it's in sequential order. So when we build our ACLs, we want to make sure that we keep that in mind, the sequence of how it looks at the ACL to filter, to permit or deny traffic. Another thing, you're going to see ACLs always have a permit any as the very last access control entry, the very last statement in that access control list. Why? Because if I don't have this, there's what's called an implicit deny at the end of every access control list in Cisco iOS. So if I have an access control list that's permit 1.1.1.0, that's permit 2.2.2.0, and I leave it at that, all other traffic is going to be denied, okay? Because there's an implicit deny all or deny any at the end of every ACL in Cisco iOS. Okay, highlights, what to remember from here is that standard ACLs, remember the number range, okay? 1 through 99, and then 1,399 to 1,999. Another thing to take, if you're taking notes, is standard ACLs only filter on source IP, and we need to place that standard ACL as close to the destination as possible. Destination being whatever our security standard is that we have to enforce. If it's deny traffic to whatever the case may be, put that ACL as close to that destination as possible. Okay, extended ACLs. So extended ACLs give network administrators way more granular control. Because now with extended ACLs, we don't filter just based off source IP. We filter based off source or destination IP, or source port, destination port, or source port and destination protocol, or a combination of all those. So it allows for filtering based on protocol and port numbers as well as IP addressing. So when we build an extended ACL, typically we say deny TCP or deny UDP. Or we could say deny IP as well. We can still just do, hey, look at the layer 3 header, not the layer 4 header. But that's how we build extended ACLs. So in this case, we have the same security standard. Guess what? Now we don't have to deny just based off a whole network. We can say, hey, this whole network just can't do SSH to this destination. And we get a lot more granular control. So with that control, it also changes the best practice on where to place that extended ACL. Now we want to place the extended ACL as close to the source as possible. Because in this previous one, since we placed it here, guess what? Now if we like put a user here that we can't even HTTP here anymore. We can't even do HTTPS to those servers anymore. With extended ACLs, now we can be granular. Now we can say only when a user tries to SSH those servers will we deny it. And you see that in this little pseudocode. It's saying deny that source network to this network. So we're denying traffic from here when it's destined to here. And we're only denying traffic with port 22, essentially, and the layer 4 header, SSH. Another key note is the numbers. Extended ACLs, when we're not doing name configuration, are 100 through 199 and 2000 to 2699. Okay, now named ACLs. So named ACLs can either be standard or extended, and it's just the syntax, okay? It's how you can edit the ACL on Cisco iOS. Give me 1 second here. I'm going to console into a router real quick, and I'm going to show you what I mean by extended versus, numbered ACL versus a named ACL, okay? So I'm in my router right here, and this is in our EVE-NG environment. And for you guys in my Zoom chat, my Zoom class, you still have access to the labs today till about 8 p.m. So if you have anything you want to go over, feel free to access those labs. Okay, so I'm going to do just something real quick, just so our syslog messages don't pop up on us. All right, so when I create an ACL access list, I do question mark, you can see this is telling us the numbers, what they're used for. So if I do access list 90 permit 10.0.0.0 wildcard mask /24 and I hit log at the end, this is a standard ACL that's numbered, okay? All right. But if I want to do an extended ACL, I can just put an extended number, and then I have to do permit based like TCP 10.0.0.0 with the wildcard mask. And we'll say to this network 192.0.0. So whatever we're doing, we're permitting this traffic to go to this traffic. So source to destination. And then we have to pick the port or protocol. So we'll say SSH. Actually, we have to say equal to. And then sometimes it'll let you do this. Like you can type in web, which was like port 80. We'll do just port 22. Okay. Now, that's how we just do standard or extended. But if you want to do named ACL, check out the syntax. It's IP access list. And then we give a name to it after we choose what type it's going to be, standard or extended. So we'll do extended here. And then we give it a name. I like this a lot better because you can say what it's for. So if this is like filter, telnet, traffic, we can put that. And then here we do our statements, our permit or deny statements, okay? So that's the difference between when we're just building a standard or extended ACL with the number versus name mode. We get this sub-configuration mode here, okay? Alrighty. So why we use ACLs? So obviously to filter traffic, but there is some other use cases for them. It could be just to define traffic. So we can use ACLs to just define traffic. Like let's say we need to define traffic for like port forwarding, like NAT address translation. We use an ACL. So here we see I use this ACL for standard NAT, and that's the named access control list I use to define the traffic that I'm going to use in this NAT statement here. So the filtering logic in sequential order, and there's an implicit deny at the end of every ACL. Talked about this. And then here's the configuration. Here's how we can verify. So we can do this command show access list. And if we do that log command at the end of each of our access control entries, our permit or deny statements, we'll be able to see if we are matching against that statement, which is pretty cool. Okay, so that is ACLs. Alrighty, moving on. Now let's get into security. So now I'm going to talk about layer 2 security. Well, ACLs is part of security as well, but we're going to get into layer 2 security. So this is things we can do to protect our campus network against like insider threats or any malicious actors from within, okay? Let me just bring some stuff up here. Okay. So on the agenda for layer 2 security, we got a lot to go over. So we have just a general overview of layer 2 security, and then we're going to go over the actual techniques and protocols, technologies we use to defend our campus network against basic attacks like rogue access, rogue DHCP servers, rogue ARP spoofing, okay? Different types of frame flooding attacks, things like that, okay? So, securing our layer 2 infrastructure is a very important component when designing and configuring LANs and the campus network. We want to mitigate threats, malicious actors, and this should just be part of our baseline, okay? When we're deploying switches, access switches, distro switches, we want to build layer 2 security into our baseline. So to ensure we take a defensive depth approach from the security perspective, our role as network engineers is going to be to enforce these different layer 2 security mitigation techniques. So there are many technologies we can implement in our switches. So we have control plane policing and protection, which isn't part of the CCNA, but I wanted to put it in there. We have DHCP snooping, which protects against rogue DHCP servers. Dynamic ARP inspection, which protects us against ARP spoofing. We have private VLANs that we can use to isolate or quarantine. We have storm control, which is just preventing broadcast storms, which is like spanning tree. Anyways, we have BPDU guard. So BPDU guard, some spanning tree protocol, can prevent any rogue user from putting a switch on the network or setting superior BPDUs and making themselves the root switch, crazy things like that. We have VACLs, or VLAN access control list. And then we have port security, which is only allowing certain amount of MAC addresses on an actual switch port. And then we have probably the most complicated of this list, network access control, which is utilizing protocols like 802.1x and Radius to actually create a whole ecosystem using like a AAA server like Cisco Identity Services Engine to do network access control. So when users plug things into a wall jack, we have a whole robust role-based access control, LDAP integrated, license on your computer control system to the enterprise. Okay, now, jumping right into it. I'm going to take a little water break here. Okay, DHCP snooping. So DHCP snooping protects our LAN architectures by providing protections from DHCP-based attacks. So the goal of DHCP snooping is to authenticate which interfaces should accept DHCP messages and which shouldn't. So essentially what we're saying here is that we know the DHCP process, DORA, discover, offer, request, acknowledgement. The discover and request come from users, and those are broadcast messages. But the offer and acknowledge messages in DHCP should only come from our legitimate DHCP server. So an easy, call it a hack or malicious attack, is for somebody, a rogue user out there, to have a rogue DHCP server which responds to those users' discover messages. It's a broadcast, right? So everyone receives that DHCP discover message. And if that rogue DHCP server responds, we want to mitigate that. We want to mitigate this by only allowing which we know is the legitimate DHCP server to respond to those DHCP discover attacks. So DHCP snooping will filter only DHCP messages, and it uses trusted and untrusted ports to either allow or drop DHCP messages. So by default, when we enable DHCP snooping, all ports are untrusted. So untrusted ports can only accept DHCP client messages, okay? Trusted ports will allow interfaces to receive and transmit DHCP server messages. Really, that means all messages, right? So what we mean by this is essentially, by default, when we enable DHCP snooping, that already just stops any rogue server, but also stops a legitimate server, right? So now what we need to do is figure out on which interfaces is the DHCP server going, are we going to receive DHCP server messages? So if R1's our DHCP server, it's going to respond to that DHCP discover message with a DHCP what? Offer. And that DHCP offer message should only come from the server. So now we look at our switches and we say, okay, on all my switches in my architecture, which interfaces on those switches should be receiving inbound ingress a DHCP server message? Well, that's going to be this interface here and this interface here. So those are the only two interfaces that I need to configure to be trusted. Yes, that offer message comes out here and it comes outbound here, but we're looking ingress because that's how DHCP snooping works, is that we will allow ingress DHCP server messages on trusted ports. Now, when this rogue server sends a DHCP offer message, because it's trying to become the DHCP server, it's rogue, it's a malicious attack, this is an untrusted port. So what's going to happen to it? It's going to filter that, okay? And that's DHCP snooping in a nutshell. I mean, I really don't want to describe it any further than that. The kind of attacks we're protecting from, starvation, poisoning attacks. We don't need to dive too deep into it. But we will go over basic configuration, even though it's not technically on the exam. And this is it. So we have, to activate DHCP snooping, we type in IP DHCP snooping. And then we say what VLANs want to, do we want to do DHCP snooping on. And then by default, everything is untrusted. So what we have to go in to do now is just choose which ones are going to be trusted. And that's it. If you guys want a more in-depth explanation where I dive deep into these other slides here about the snooping operation, because it can get a little bit more complicated than I'm making it out to be for testing purposes, I went over everything you need to know to be successful in the exam, okay? But you can check out our YouTube channel. And then verification is show IP DHCP snooping binding. Okay. Missing one. I want to go over dynamic ARP inspection. There we go. Okay. Now, let's go over dynamic ARP inspection. So this is another layer 2 security technique or mitigation technique. And this actually builds off DHCP snooping. It needs that DHCP snooping binding table to be able to use dynamic ARP inspection. So how I taught it is actually in the order of how you configure it. So you have to configure DHCP snooping first, because on those switches, we're going to have a DHCP snooping binding table, which is going to show us the correct layer 3 to layer 2 mappings between IP to MAC address. And then dynamic ARP inspection, the technology is going to use that binding table to ensure that we don't become victim to an ARP poisoning or ARP spoofing attack. So on the agenda, we're going to go over dynamic ARP inspection. We're going to do a quick ARP review and gratuitous ARP review. We'll go over ARP poisoning and what kind of attack it is, and then how DAI actually works. So dynamic ARP inspection protects our LAN architectures from malicious actors manipulating the ARP process. So this is a security feature that's enabled on switches and only affects ARP packets. That's all it's looking to do, protect us against any malicious ARP attacks. So DAI will use a DHCP snooping binding table to verify layer 3 to layer 2 mappings. Now that's a typical configuration. We could also do dynamic ARP inspection using static ARP ACLs. So that's another way we can achieve DAI without using the DHCP snooping table, but it's just, two different ways to do it. I've always done it. I've done both, actually. Done both on a network. So DAI inspects and filters ARP messages on untrusted ports. All ports are untrusted by default when DAI is enabled, much like DHCP snooping. That's the default state. So quick little review. So the address resolution protocol is used to map layer 3 to layer 2 addresses in our network. So endpoints and network devices will store this mapping information in what we call the ARP table. Now, like routers do this as well. Switches will have a little ARP table as well. Let me show you guys an ARP table real quick. Hold on, I'm bringing this up on my computer. So you can see, like in my terminal here, I did this ARP command, ARP-A, and it shows me my default gateway's MAC address. So it does that layer 3 to layer 2 mapping, okay? It shows me this user here that I've communicated with, their MAC address. So that's what ARP does. So ARP gives us the ability to build that full packet with the layer 2 header when we're talking to our default gateway, and it gives us that MAC address to put in the destination MAC address field. Okay, a gratuitous ARP. A gratuitous ARP is an ARP reply packet that's broadcasted out to the LAN. So that's like if my computer wants to tell all the other workstations on my broadcast domain, hey, this is my MAC address, we do a gratuitous ARP. So pretty much we send an ARP reply packet to everyone, and then they take that reply packet, put it in their ARP cache, and say, hey, 192.168.100.50, which is my workstation, its MAC address is this, okay? And that'll go to all users. So ARP poisoning, that's just a man-in-the-middle attack that manipulates the ARP tables of devices and tries to point you to that whoever that malicious user is, trying to say, hey, I'm the default gateway. So DAI operation. So how does dynamic ARP inspection actually protect you? So this will inspect the sender MAC and the sender IP address in the ARP packet and compare it to the DHCP snooping binding table. And if the MAC and IP address match, the ARP packet will be forwarded. So pretty much we're just verifying. We're verifying that no malicious users are trying to say that they're actually the default gateway, okay? So DAI will only inspect on untrusted ports. DAI relies on DHCP snooping to be enabled, but can also be manually configured using an ARP ACL. And here's the configuration. It's very simple here. So it's just IP ARP inspection on whatever VLAN you have. So if you have 10 different VLANs for your users, we're going to do this on 10 different VLANs. And then we have trusted ports that we need, and that's going to be between network devices. So if you get a question that's like, what kind of device will be connected to a dynamic ARP inspection trusted port? It's going to be a network device, okay? And here's just, we can put rate limiting as well. And here's that show command, show IP ARP inspection interfaces. It'll show you the different trusted states, the different rates, pretty much how many packets are we inspecting. That's when we say by rate. And there we go. That's dynamic ARP inspection. Okay, moving on to a different layer 2 security protocol. Now we're going to go over port security. Okay, so port security is going to be another layer 2 security protocol. So port security on switches is going to protect our LAN infrastructure from rogue devices that are doing pretty much MAC address-based attacks like MAC flooding. Port security allows you to configure how many MAC addresses can be allowed on a switch port. What I want to do real quick here, guys, is I'm going to SSH to my Cisco Catalyst 9300 switch I have here, so we can maybe see some port security configuration. Okay, back to the slides. So port security is going to give us control over our network access by limiting the amount of devices that can be connected to a single switch port here. So you see some pseudocode here essentially saying, hey, only one MAC address is allowed on this port, and if we get more than one, we're going to shut down that port by putting in what's called an error disabled state. So why do we need it? So switches make forwarding decisions based off destination MAC address. So we have a CAM table that's built using source MAC addresses, and that's the forwarding table that we're going to reference when we need to forward frames. So switches do have a limited amount of CPU and space available for that CAM table. Very limited, because we use ASIC chips on our switch ports to actually do most of our data plane compute functionality. So malicious users can exploit the limited resources of a switch by flooding the switch with fake MAC addresses. And then we pretty much do almost like a denial of service attack on that CAM or MAC address table. Okay, so port security is configured on access ports. You don't configure this on any trunk ports, okay? And once enabled, port security by default will only allow one MAC address per interface unless we do additional configuration. And if port security is violated, so whatever, policy we have on there, like permit 1, 2, or 3, it doesn't matter. Once that policy is violated, we're going to send that port into an error disabled state, which will shut that port off. Okay, so here's the security violation modes we have: protect, restrict, and shutdown. Shutdown's the default mode. So we have additional options for port security. We can allow it to save MAC addresses that it learned into the running config, because naturally our MAC address table will be flooded every 300 seconds or 5 minutes. But we can do something called sticky, which will make the source of MAC address learned to be saved into the running config. So even in an event of a reboot, that port, that switch port will say, hey, no, I only need this MAC address. I can only allow this MAC address on my port. So here's port security configuration. The basic configuration is we need it to be an access port, and then it's switch port security. If we leave it at there, only one MAC address will be allowed on that interface. And if the security violation mode by default will be shut down, which means we're setting that port straight into an error disabled state if we get more than one MAC address learned on that port. Some verification. So we do show port security. It'll show us how many security violations we have and the security actions. And then here's some more advanced configuration. So there we can change how many MAC addresses we want allowed. This is pretty common. We have a VoIP phone and a phone tethered off that VoIP phone. We can also do sticky, which is going to memorize the MAC address on there and put it into the running config. We can also change the violation mode. We can also say, hey, we can statically set what MAC address should only be allowed on that port as well. We want to clear port security. So we want to clear the error disabled state once a port security has been violated on that switch port. We just flap it. So we flap that port by shutting it and then no shutting that interface. Okay. So I just want to show you quickly this configuration. So if I do this, switch port security, maximum 2. And I type in do show run interface gig 6/0/20. So it looks like I might be able to do port security. But if I type in do show port security, gig 20 is not part of that table. Well, why? Because this is the actual command that activates it. Okay? And now port 20 is a part of it. So we need that command, switch port security, that actually activates it. Even if I do all this additional configuration, if that's not there, port security ain't working, okay? Alrighty. Now let's move on. Let's go over some wireless security. I'm going to take a little 1-minute water break, okay? Whew, yeah, this is definitely a cram session, going quick. Hopefully you guys are getting something from this. I'm also live streaming this on my YouTube channel, so like, you can go watch this video back. I'm going to save it. Okay, let me get this one up here. All right, now let's go over wireless security. Now, like I said, we can get pretty deep into wireless security. So I can get into how we do authentication, how we do integrity with like HMAC and the different EAP frameworks, our extensible authentication protocol frameworks we can have for our Wi-Fi authentication. But really, guys, I just want to go over these standards with you because that's going to be important on the exam. So wireless security fundamentals. So wireless local area networks use Wi-Fi RF signals to connect Wi-Fi enabled devices to the switch network. These signals are broadcasted, so anyone can connect to them if they were open. There's not this inherent protection like our wired network, which you have to plug in and we have all this network access control capabilities. So since these Wi-Fi signals are openly broadcasted, we need to protect, encrypt, and authenticate this traffic when they're connecting to our wireless local area network. So the three main concepts we're going to cover is authentication, encryption, and integrity. And again, I'm going to quickly go through authentication. Now, we're going to skip all this. It's just not very important. Go check out the actual YouTube playlist if you want to dive deep into this. So here's all the authentication methods I do go over in that YouTube video. It's like a 2-part series. But here's open authentication where we don't have any authentication at all. WEP, wired equivalency protection. That was the very first protection we ever had on Wi-Fi, and this is vulnerable. If you ever want to do some like wireless hacking labs or like wireless penetration labs, get an old access point, configure WEP on it, and that's how you really learn how the fundamentals of Wi-Fi, by breaking it and like cracking web. It's pretty fun. Okay. So we have EAP. This is an authentication framework that we can build on top of. I'm going to quickly go through this, guys. Okay, so now let's go over the different encryption methods. So we have two different encryption ciphers we're going to use in wireless, okay? So we have TKIP. That's a temporal key integrity protocol. This is an encryption method used in wireless networks to secure the data transmitted between a client device and an access point. So this was like the next step in web, adding actually encryption. So changing those 802.11 frames from plain text to ciphertext. Main thing you got to know with TKIP is that it's vulnerable, okay? This cipher suite, this Wi-Fi encryption is vulnerable. Now, TKIP was typically used in conjunction with WPA, Wi-Fi Protected Access. The very first evolution of it typically used TKIP. So on the exam, TKIP is vulnerable. We don't want to use it for security. Then we moved on to CCNP. So the counter mode with cipher block chaining, message authentication code protocol. Whew, you don't even memorize that acronym for the exam. This is an encryption method used in wireless networks to secure data transmission between our clients and access points. So CCNP, when we moved on to the next evolution of WPA, when we started using WPA2 and even WPA3, CCNP was our cipher suite that we used to actually use encryption. So it's a block cipher that uses AES. Excuse me. So CCNP employs the advanced encryption standard. This is a symmetric encryption algorithm, and this is thanks. This is what we're actually going to use for WPA2 and WPA3. This is going to give us our data packet encryption. So with CCNP and AES, we're going to have different bit key lengths, okay? So AES comes with 128, 192, and 256 bit key lengths. Now, why am I saying this and what do you need to know about this? You just need to know that it comes in these different lengths and that the original standard, hear my words, the original standard when this first came out, I think it was like back in 2011, was just 128 bits, okay? Was just 128 bits for CCNP with AES and WPA2, okay? But then as we advanced, even with WPA2, we could use this cipher suite with these higher bit key lengths, okay? Now, the longer the bit key length, the harder it is to crack that encryption. So the stronger the encryption is, okay? Okay, and then we have GCNP. So GCNP came out, and this was used with our WPA3. This is the next evolution of our Wi-Fi protected access, WPA3. This is currently, when you go test for CCNA, right, the strongest method of protection for Wi-Fi we have. And it uses GCNP, which is the Galileo's counter mode cipher block encryption message protocol. Whew, okay. So with GCNP, we're still using AES. And again, we still have those bit key length standards. So what was the improvement? Well, obviously we use GCNP now instead of CCNP. But WPA3, actually just WPA2, WPA3, and regular WPA has two different ways to authenticate you onto the wireless network. And that's using a pre-shared key or enterprise. So remember, this is just the encryption cipher that's used, but what's our different WPA modes? PSK and enterprise. So with PSK, that's where you send a single password to connect to the Wi-Fi. That's when you go home. Hey, can I borrow your Wi-Fi? Your buddy comes over, you give him a password. Okay, that's pre-shared keys. Enterprise. Enterprise is when we actually have some sort of AAA or authentication server that's hosting credentials, and you need credentials to be able to log into that Wi-Fi, okay? Why am I saying this? With WPA3, for PSK, for WPA3, I'm going to write this down here. We have some advancements. We use something called SAE, Simultaneous Authentication Equals, to protect against brute force attacks, by giving us the ability to have perfect forward secrecy, okay? So that's an improvement with WPA3 along with using this better cipher suite. So I'm going to move on real quick because I think I have a slide that covers that, so I might have got ahead of myself. Okay, so the Wi-Fi Alliance has developed 3 WPA certifications for wireless devices, WPA, WPA2, WPA3, and it comes with 2 authentication modes, personal mode and enterprise mode. Personal mode, yeah, also WPA2, PSK is what you're going to see in the actual GUI on a wireless LAN controller when configuring WPA security and you're picking a mode. So WPA, the encryption used was TKIP. Enterprise mode, we use AAA, Radius, 802.1x to actually authenticate. And then personal mode, we use PSK, pre-shared keys. With WPA2, we use CCNP and AES as the encryption. And that's the encryption that's used for both these modes, okay? Now, WPA3 had those advancements where we used still AES, the advanced encryption standard, for our symmetric key algorithm. And then our cipher suite, we use GCMP. And then for personal mode, we got additional protections added on using simultaneous authentication at equals for secure key exchange. This gave us perfect forward secrecy, okay? To ensure that even if one session's key is compromised, it cannot be used to decrypt past or future communications. So it's protected us against like brute force attacks, okay? All right. That is wireless security. I know we're moving quick. Now, let's go over AAA. So AAA, now, as much as like in my heart as a network engineer, I would love to show you guys how to configure a TACX or Radius server using Cisco Identity Services Engine and see how to integrate it into Active Directory to start giving us role-based access control or mandatory access control. When people want to configure, want to get access to our network devices, or we want to authenticate a computer onto the network using ICE, using Radius, putting licensing on those computers. As much as I'd like to show you guys all that, which is all part of the AAA like ecosystem, we're going to be basic here, okay? We're going to just go over AAA overview, operations, and the different protocols that'll give you success on the exam. So what does this acronym stand for? Authentication, authorization, and accounting. So AAA provides our networks with secure network access, control and enforcement, usage monitoring, and accountability. So AAA plays a crucial role in providing secure network access to authorized users. Through authentication, it verifies the identity. Through authorization, it verifies permissions and set permissions and what you can have access to. So by implementing robust authorization policies, AAA ensures that only authenticated users with the appropriate privileges can access network resources. So we have AAA servers like ICE. We can identify and authenticate based off someone's credentials. We can authorize. What do they have access to? What's their permissions? And with that, we always go with our best principles, right? Role-based access control, maybe some attribute access control. Principle of least privilege is going to determine our permissions settings and our security policies. AAA enables network administrators to enforce granular access controls and policies. It allows administrators to define who can access specific network resources, applications, or services. It also has usage monitoring and accountability, so the A, accounting. So that lets us do some sort of auditing functionalities. So it lets us track network resource usage. Lets us track who's logging in and what they're doing into our network devices. It records information such as user activity, session duration, and resource consumption by that user. So the authentication part. So AAA's authentication operation verifies the identity of users or devices attempting to access a network. It ensures that the entity requesting access is who they claim to be through through multi-factors of authentication. Either your username and password, a digital certificate, biometrics, tokens. So authentication establishes a user's identity as a prerequisite for accessing network resources. Authorization. So AAA's authorization operation determines what actions, resources, or services a user device is allowed to access. It's going to grant or deny permissions based on the user's authenticated identity. So role-based access control, right? And what they should be doing. accounting. So AAA's accounting operation tracks the usage and activities of authenticated users or devices in the network. So different AAA protocols. We have TACX and Radius. So TACX is a Cisco proprietary protocol. Port 49? I think that might be a typo. Hold on. Let me look this up. TACX port number. Yeah, 40. What am I thinking? Yeah, that's the right port number. Sorry about that. I'm doing this Cram session, going through a lot of stuff. Anyways, so TACX is a Cisco proprietary protocol that uses TCP port 49 to deliver TACX packets. So with TACX, we are going to have a TACX packet for each operation in AAA. We'll have an authentication packet, an authorization packet, and an accounting packet that we can encrypt as well and do authentication on all three of those packets. With Radius, we use it's open source. For one, it uses UDP ports 1812, 1813. With Radius, we're going to combine the authentication authorization packet into one, with the accounting packet being separate. And that's AAA. So before we take our next break, there's a lot I could go over with WAN architectures. MPLS is not talked about. How your cable TV connection is not talked about in the test. This used to be part of the CCNA, like going over these definitions, multi-home, dual-home. But really, they just talked about VPNs. So that's what we're going to talk about, okay? So yes, I'm jumping right into the middle of a slide deck. We're going into VPNs. So you guys know VPNs. Actually, one second, guys. Let's go ahead and take a 5-minute break. Okay, sorry for just abruptly stopping there. I had to take a pretty important phone call from the contract. Okay, VPN, so virtual private network. So you guys probably know all about VPNs. Once TikTok gets banned, you're going to VPN into Canada, right? From your phone, VPN's just, it's a simple way to get some encryption from the phone to whatever you're accessing. You know, they always say you go on Starbucks Wi-Fi, put a VPN in. They leverage the public internet infrastructure for secure encrypted communications. Now, VPNs originally were like an enterprise solution, meaning that we created VPN so that if we had a remote site, we could connect that remote site in Phoenix back to our headquarters in New York with a direct connection and give users their access to our intranet through this VPN connection, okay? So tunneling was originally just like our layer 2 point-to-point tunnel. So these VPNs create tunnels within the public internet, encapsulating data packets to prevent unauthorized access. These tunnels facilitate secure data transmission between remote locations as if they were directly connected on a private network. We have a bunch of different VPN protocols. We have IPsec, which is typically used in a site-to-site VPN. Then we have SSL TLS, which is which was used a lot for remote access VPNs. That's what's used for HTTPS, right? So you can think of your client-server web architecture almost like a VPN. You're directly connecting to the web server, right? And through the internet, you're protected. We have point-to-point tunneling protocols. I use WireGuard. That's my VPN of choice. I got a WireGuard VPN set up here at my office. Let me share this a different way because I might want to write on it. Okay. So the first type of VPN we're going to talk about is site-to-site. They're created and used for enterprises with multiple offices that need direct connections to each other or a hub site. So site-to-site VPNs are typically used / configured on a stationary network infrastructure. Site-to-site, what we're meaning here is that this is not your remote access user out there working from home or on a plane or at the coffee shop. This is like, I have a site in Fayetteville, I have a site in New York, I have a site in Phoenix. New York's my data center, and we have dedicated network infrastructure there, firewalls, routers, and they're going to be creating connection to them. That's a site-to-site. So that's router to router, router to firewall, router to VPN concentrator, and then, firewall to firewall. I don't need to say all those. Remote access VPNs, those are for our remote users. So that's where a VPN application gets installed on like the operating system on your Windows computer, and you activate it, and it connects your Windows computer and that NIC to a VPN service. So site-to-site VPNs connect two or more geographically separated networks securely. Sites, right, I like to call them. Site-to-site typically uses IPsec. That's going to be, that's a standard CCNA wants you to learn about. So IPsec VPN and Cisco. So Cisco uses the Internet Protocol Security, provides secure encrypted tunnels between Cisco devices for site-to-site remote access VPNs. Remote access VPNs, I guess you can use IPsec, but that's not common. I wouldn't say it's a standard. IPsec VPNs in Cisco have two main components, the Internet Key Exchange Protocol, and then we have the Encapsulating Security Payload Protocol. The port numbers for that, if you ever need to allow them in on a firewall, is 500 and 4500. And we have two modes for IPsec. I am going to literally end. This is what you need to know for the exam. I'm going to go over this, and then we're going to go on our next break to get into automation, because this is what you need to know. So site-to-site IPsec, we have transport mode. So if I configure transport mode, you can see my data payload's encrypted. We're authenticated, but my IP header is exposed. My original IP header is still exposed. With tunnel mode, we actually encapsulate our IP header. Well, it's encapsulated there, but it's exposed. Anyways, and our original IP header is encrypted and protected. Okay? That's the difference between these two. Transport mode, your IP header is exposed. With tunnel mode, your original IP header is encrypted. So on the exam, if they ask you, which mode encrypts the entire IP packet? The entire IP packet, it's tunnel mode, okay? And yeah, we don't need to go over DMVPN or GRE. It's not on the test. It's at least not on the exam objective, so we're not going to talk about it. Okay. I need to give my voice a rest. We're going to come back at 11:40 East Coast time. And we're going to jump into JSON and REST APIs. And then we're going to be done for the day. I'll get off my YouTube live stream and talk to you guys in my Zoom class. Just some reminders about shit, okay? Let's come back at 11:40. Okay, guys, let's go over this last section for today. So let's just go over some network automation overview. So what is it? So network automation is a new way of us looking at our network compared to traditional networking where we individually manage and configure network devices. So network automation, controller-based networking, software-defined networking, kind of all in the same vein. It's a way to automate, centralize things for our network. So task automation. So network automation involves automating a wide range of networking tasks. It's configuration, management, updates, monitoring. It gives us consistency. So by automating things, we look at our entire network as a single code base. It allows us to not have configuration drift. Allows us to all be on the same baseline and configuration for all of our devices. And that helps us with a lot of compliance and other things within our industry. Scalability. It helps us be more scalable. Easier for us to spin up network infrastructure. That could be on-prem or even in the cloud. Automation helps us to build that scale. It gives us a programmable infrastructure. So with routers, switches, firewalls, they often come with APIs, and they have a southbound APIs that allow us to interact with them via more modern ways like HTTP or REST. It gives us orchestration. So, network automation allows us to orchestrate our network. So network automation can be implemented through scripting languages like Python, Ansible, using the NetMiko library. That's the most popular one. It's kind of the only one. We have Paramiko and other things, but NetMiko is the main library. And then we have this concept DevOps or Net DevOps. So it's closely related to development and operations and Net DevOps methodologies. Cloud and SDN integration. So network automation extends into cloud environments and software-defined networking solutions. So like networking in the cloud, we can use things like Terraform to spin up VPCs and VNets in AWS and Azure respectively, and network infrastructure like that. SDN is going to give us a lot of telemetry. It gives us continuous monitoring and feedback and splits our architecture into an underlay, overlay, and a fabric. We have security and compliance. So automation can enforce security policies and ensure compliance with industry regulations a lot easier and in a more efficient way. So let's go over some, you know what? We kind of already talked about this. So sorry if you're watching on YouTube, but we went over control plane, data plane in our class already, so we don't need to touch on it again. This is a cram session. So software-defined networking or versus traditional networking. Think of SDN also as controller-based, okay? Controller-based as well. So traditional networking, you have distributed control. So in traditional networking, control plane functions are distributed across individual network devices. You have static configuration. So in traditional networking, network configuration is typically static and device specific. Changes and updates often require manual configuration. Complexity. So managing and troubleshooting networks can be complex as network administrators need to configure and maintain each device separately. So we have increased complexity with traditional networking. Software-defined networking or controller-based networking. This is going to give us centralized control. So SDN centralizes network control by separating the control from the data plane and putting all that control plane into a single device. Automation and orchestration. So SDN can facilitate automation and orchestration of basic and repetitive network tasks. It's dynamic and programmable. So SDN networks are highly dynamic and programmable from a programmer's perspective. We can use HTTP, REST, and APIs now to configure and manage our network. It also, once you learn it, simplifies the management. So SDN simplifies network management by providing a central point of control. This abstracts any network complexity, making it easier to manage and troubleshoot issues. So traditional networking right here. This would be software-defined networking, okay? Where we have our controller with that centralized control plane, and then we have our GUI, our interface here, that's either directly interfacing with like a Cisco Catalyst Center, an SD-WAN, or sending requests, okay? And then that gets pushed down to our data plane here, which is our fabric. So we have application programmable interfaces. So an API. This is, actually, you know what? We're going to skip what an API, the definition of it is, okay? But it does facilitate data exchanges between programs because we're going to go over that in our last slide here a little bit more granularly when we talk about REST APIs, okay? Let's go over something called southbound and northbound interfaces. in SDN, because you may be asked about this. So a southbound interface in networking refers to the communication link or interface through which instructions and commands flow from network controller or management plane. So like a southbound interface would be our Cisco Catalyst Center getting information from our fabric, our actual routers and switches. That's an SBI, a southbound interface. So SBIs allow the network controller, which is typically part of an SDN solution, to send specific instructions and configuration or to get information from our network devices, our fabric, our actual hardware. So the protocols, what is the actual technology used in southbound interfaces from the controller to our fabric underlay, to our south? We're going to have standardized protocols like netconf and restconf that have to be enabled on the actual router or switch to be able to communicate via restconf and netconf between the controller and our underlay here. Northbound interfaces. So the northbound interface is going to be the communication link or interface through which information, data, and request flows from network application services or external systems toward the network controller. So that is us right here, sitting on our development computer, interacting with that controller. We're sending northbound interface requests, which is going to be like REST methods. It's going to be REST requests, doing GET methods, doing POST requests. So this northbound interface enables communication between application services and external systems to our network controller. These interfaces allow applications to send requests for network configuration, status updates, or information about the network state. So we can send a GET message down to the controller that says, hey, we want to learn about this site's switches and their management interfaces. The controller converts that to RESTconf, sends that request down to the router. The router responds with the RESTconf response to the control plane or the controller. That's going to send the HTTP request back to the application. It's going to be structured in our standard data serialization like JSON or XML back to us. And all that process is done by us sending that GET request down, which is the northbound interface. So protocols and standards in our NBIs, our northbound interfaces, are RESTful APIs, REST, gRPC, and other custom APIs we may build. Okay, now let's talk about the common data serialization that we're going to use, which is JSON. Just to touch on this, guys, on the exam, if they ask what is a southbound interface, what kind of protocol can be used, that is RESTconf, netconf. If they ask what does a southbound interface enable communication between controller and hardware, controller and network, the actual network infrastructure, network appliances. They talk about northbound interfaces and what does it enable communication to? That is the controller and our applications and services. A northbound interface enables communication between the controller and our applications, okay? And that's going to be using like REST APIs. Key notes there, okay? Key notes. Now, let's go over JSON. So JSON is going to be the standard way that we structure data and it gets represented to us. So let's talk about data serialization. So structured data. So in network automation, you often work with structured data that represents configuration commands or status information of network devices. This data can be in the form of dictionaries, JSON, YAML, or XML. So data serialization languages allows us to represent variables with text and that can be recognized between different devices. So JSON is recognized in our databases, our backend servers, our front-end web servers, our network devices, and our controllers can all understand JSON and can all format information into JSON. So JSON stands for JavaScript Object Notation. It's a lightweight, human-readable data interchange format that can be understood between, again, all those things I just described. It's widely used in network automation, and it's used really in everything, right? Our monolithic web architecture and our microservice web architecture. The whole internet exchanges information via JSON. So JSON is often used to represent and exchange structured data between different systems, making it an ideal choice for network automation purposes. So the structure of JSON. So JSON data consists of key value pairs. Keys are always strings enclosed in double quotes, while values can be strings, numbers, Boolean logic, false, true. Value can also be in a nested JSON object. It could be a nested array, or it could be even a null value. So JSON objects are enclosed in curly braces, and key value pairs within them are separated by commas. JSON arrays are ordered lists of values enclosed in square brackets. So let's interpret JSON. I'm going to interpret this large image here, and then I'll go over that one in the previous slide. So if I get, let's say this is line 1, this is line 2, 3, 4, this is line 5. So if I ask you, what is the value in line 3? Maybe how they want you to interpret JSON in the exam. Let's go over this JSON structure. So when we have these curly braces, that represents a single object with an open and closed brace. That's a JSON object. JSON objects have in them key value pairs, with that key, kind of almost like, think of it as a variable, that key equaling this value. So the value of this key interface is gigabit Ethernet 00. So when you see these quotes followed by a colon, and there's always a string in here, we're going to go over what a string is in a second. That's a key. The key is always followed by a value. I don't know how to spell today. Okay. Now a value can be a string. So a string is just a regular word. It's just regular characters in quotes. A value can also be an integer. So this is a number, not in quotes, okay? This can also be Boolean logic, which just means true or false. So this one down here is up. So the key is up. So is the interface on? It's either true or false. It's either on or off. On, off. True or false. 1 or 0, right? Boolean logic. A value can also be another nested object. So what we're saying here is that you could have this object with this key, and then the value could be another JSON object, another nested object. Okay? So this right here is Boolean logic. It's true or false. This right here is a string value, and they're all values. This is a value. This is a value. This is a value. This is also a string. This is a value. And notice it's the last key value pair in this JSON object, so there is no comma. The last key value pair in a JSON object does not have a comma. And this is an integer. Okay? That's how we interpret JSON. So to answer that question, what is the value in line 3? It's a string that equals full. Okay? Now let's go back here. So if I'm looking at this JSON object, how many objects are in this entire JSON object? So we have 1 open bracket, 2 open, 3, 4. So we have 1, 2, 3, 4 objects in here. Because an object, a JSON object, is represented by an open curly brace and a closed curly brace. So break this down even further. This key here, interface underscore configs, its value is a JSON array. And in that array, we have nested JSON objects. So in that array, we have 2 JSON objects. Okay? So in this case, if this is, again, I put the line numbers. If I ask you, what is the value in line 4, it's another object. The value for the key interface underscore configs is a JSON array, excuse me. It's a JSON array, which has 2 nested JSON objects, okay? Now down here, you're maybe wondering, is that an array? That's a list. So a list is a bunch of strings. It's a little confusing there. I need a new example here because that throws people off because they're like, that's an array. It's actually a list. So that key value pair, the key networks, the value is a list of strings. Anyways. Okay. So that's how we interpret JSON. You need to understand how to interpret JSON for the exam. Now, to finish this off, let's go over REST APIs, okay? REST APIs are used in our web architectures. They're also used when we're getting information via SDN from our app to our controller down to our network infrastructure. Okay, so REST APIs. We're going to go over an API overview real quick. We're going to go over CRUD operations, so operations against databases and how it relates to REST. So CRUD stands for create, read, update, and delete. Those are operations you can do against a database. We're going to correlate those to the different REST/HTTP methods. So REST is carried through HTTP, okay? The Hypertext Transfer Protocol carries your REST methods or requests, okay? And those REST methods are interacting with some sort of database information, and those REST methods correlate to CRUD operations, which are the operations you can do against a database: create, read, update, delete. We're going to go over HTTP end-to-end. So what are HTTP sessions end-to-end? We're going to go over the different HTTP codes. So 200 codes being successful, 400 and 500 codes being error codes, client and server, respectively. We'll then again touch on our REST methods, and we're going to go over which REST methods are idempotent or not. And then it says demonstration here. Not in this Cram session, but if you go to our CCNA playlist on YouTube, we have a demonstration of how to use REST to interact with Cisco DNA Center, which is now called Catalyst Center, using Postman to create the API. Okay, let's move on. So API overview. So APIs act as intermediaries between different software components, so like database and backend. They enable one application to request services or data from another application or system. So APIs provide an abstraction layer so we don't directly interface with like a database, hiding the complex internal details of a system or service. Standardization. So APIs are typically well documented and follow specific conventions and standards, making it easier for developers to understand and use them. What we mean by that is, like in REST, we have post requests, put requests that have specific things that they do. So if we need to update a database, we do a put or a post method. Functionality. So APIs can expose a wide range of functionality, such as retrieving data, sending data, performing actions on that data, deleting, updating, and more. They define methods or functions that can be called along with the required parameters and expected outcomes. Now with API security, we do want to put some security on APIs, like rate limiting or maybe authentication if it's something we don't want to expose to the public. We don't want to have a developer side to the public. So APIs often include authentication, authorization methods to ensure that only authorized users or applications can access the provided services or data. So like we do RESTful API calls to like DNA or Catalyst Center for our enterprise, we're going to have to authenticate on that. Okay, let's go over CRUD. So CRUD defines the type of operations you can do on a database. And we have a REST method that correlates to CRUD. You will have to memorize this, okay? So the create operation involves adding new data or records to a database or system. When REST does this, it's called a post request. So the REST method post creates something in a database. Then we have the read. So the read operation involves retrieving or reading existing data from a database or system. So it corresponds to querying the database to retrieve specific records or fetching data from a resource in a web application. So the CRUD operation read, when we're reading information in a database, that corresponds to the REST get method, which can request things and can also respond, right? So request or response using the get method. Now, I keep saying method here because we have HTTP and REST methods that are the same. Get, post, because REST is carried in HTTP, okay? We have the update operation. So the CRUD update operation involves modifying or updating existing data in the database. So not creating something new like post, but updating an existing table or row. So like updating your profile name. The CRUD operation update relates to the REST method put. Okay? Also another one called patch that you may see. Also patch. Then the CRUD operation delete involves deleting something from a database Guess what? This one's easy. The REST method that correlates to the CRUD operation delete, deleting something from that database, is delete. That's the REST HTTP method, delete. Okay, an HTTP request. So an HTTP request message includes several components. The HTTP/REST method, get, post, put, delete, patch, indicates the desired action to be performed on the resource. Going to a website, you're doing a GET request, right? You just want to see the information. HTTP responses from the server. So we have HTTP responses designated by a code. 1 through 500 is the different codes. So the ones you need to be aware of for the exam is going to be this code. A 200 code equals success, meaning the request was successfully received, understood, accepted, and responded to. If we get a 400 error, that's a client error, meaning that we did something wrong in our URL request or something. It's like, hey, we don't have that URL. Like, that's not real, so we're sending you a 404 error. A 500 is a server error, meaning that the request you sent was valid, but we had some misconfiguration or something mess up on our end, okay? That's the ones you need to know. 200 code are successful, 400 to 500 codes are errors. Here's a little different REST methods right there for you. So a get is a read, post is a create, put is an update, delete is delete, and patch is also an update operation. Idempotency. So idempotency of HTTP methods. Look, I don't want to dive into this definition. Just know that if they ask you, is this REST method post idempotent? What is the answer? No. If it asks you, which one of these REST methods, answers A through D, is non-idempotent, and patch or post is one of the answers, that's the answer, okay? All right, guys, that is it for this cram session. I'm going to end my stream now so I can talk to you guys on my Zoom.